Who keeps an AI agent contained when the boundary itself continues to have holes? Yesterday, Meta became the third major developer to disclose that their models had reached beyond the test environment, and then Moonshot became the first open-weights lab to disclose that their model had as well. Now here's the claim I'll stand behind. No single gatekeeper can watch the agents alone. Safety comes from making every leak visible to everyone. Come with me, let's get into it. Meta reported that Muse Spark 1.1 reached an unidentified company from inside a test environment. So how much trouble are we in? And the answer starts with the boundary. Meta's evaluation partner, Irregular, had configured the environment incorrectly. Irregular called it the exact same evaluation environment issue that was already disclosed by Anthropic last week, with no sandbox escape or sophisticated cyber action involved. So let's start with the distinction there. A sandbox is supposed to isolate whatever happens during a test. You think of it like a room with no door to the outside. In this case, the room did have a door. It was hidden, but the model found it and used it. Professor Alan Woodward of the University of Surrey put the change in perspective here. For 30 years, software testers could generally assume that whatever happened inside the test environment stayed inside the test environment. But in just over a week, that rule has broken now 3 times in major proprietary models. Now, the same pattern has reached an open-weight model as well. Frontier Security tested Kimi K3, built by China's Moonshot AI, during a UK-directed defensive cybersecurity evaluation. And Kimi found another misconfigured sandbox and followed the opening onto the live internet. It didn't hack a private system. The answers it was seeking happened to sit in a public GitHub repository. Frontier described Kimi as pursuing its objective by any means necessary. And the model also carries fewer built-in guardrails than most gated rivals. That's typically the case with open-weight models. Jaren Singer of Frontier described a leak that the model simply took advantage of. Matt Fredrickson of Gray Swan and Carnegie Mellon was even plainer. It's not surprising at all. It'll find a way to get the answer. It's a cautionary tale. Now, that is a common mechanism here across several of these cases. A human misconfigured or inadequately scoped the environment. A goal-directed system found the shortest available route. So there's no evidence here of malice, deception, or some hidden plot to break free. And again, this is the whole point of these tests, to find where humans have been inadequate in their containment measures. So that makes the models escaping their cages story a very poor description of what actually happened. The agents exposed cages that people had failed to close. Again, the whole point. The scale helps here as well. On July 31st, Anthropic reported 3 different cases across 141,006 flagged evaluations. These incidents also traced back to an evaluator's configuration. And when the UK AI Security Institute faced its own containment failure, it detected and contained the incident within an hour. That response time is really encouraging. Capability is moving quickly, and the systems watching it are learning quickly too. Each disclosed failure gives the next evaluator another seam to inspect. Kimi makes that work more urgent because it's open weight. Anyone can download it and run it and choose which safeguards to keep and which not to. No company can recall every copy. A closed review model process cannot cover a model already moving through the world. Now, independent testing and public results are the practical answer here. They let researchers and developers and defenders see the same evidence. They also prevent one lab from deciding which failures that everyone else gets to learn from. And the capability cuts in both directions, too. Frontier's work shows that open models can make a formidable cyber defense partners. Hugging Face has already worked with a Chinese open-weight model to defend its own systems, mostly because the closed proprietary ones refuse to do so because of guardrails. An agent that keeps searching until it finds a route can expose a defender's blind spot before an attacker ever does. The task now is to build environments that expect that persistence and detect it quickly and let everyone learn when the boundary fails. All right, that open door problem is about who controls the model's path. This next story moves down into the physical layer, where a handful of foundries still control the path to advanced chips. Can the world's largest chip buyers loosen that grip by making their own? SpaceX and Tesla say they plan to try. They confirmed Terafab, a chip complex in Grimes County, Texas. The first phase carries a stated price of $16.8 billion and covers 100 million square feet. And the filing says that the site would target 1 terawatt of annual compute production capacity. Musk has said that that would exceed the current global output of advanced chips. So the plan folds logic and memory and packaging and testing into one site with output intended for optimization Optimus robots, cybercabs, and eventually data centers in space, because that's what Musk is going for. Now, those are extraordinary claims, and the filing itself gives us reasons to keep them at a bit of an arm's length. The headline number was $25 billion back in March. It's now $16.8 billion. The S1, the legally scrutinized filing required before a company goes public, calls Terafab a general framework with no actual binding commitments. Reporting also indicates that Intel would handle the actual fabrication. And then there's the roadmap. On an August 5th earnings call, Musk committed SpaceX exclusively to NVIDIA's Vera Rubin architecture. That cuts Intel and AMD and Broadcom out of SpaceX's plans, even as Terafab is presented as a route to in-house silicon. So this remains a proposal layered over deep dependence on existing suppliers. Now, the local resource picture is more grounded. Terafab would draw water from the Gibbons Creek Reservoir, which is the former cooling pond for a coal plant that shut in 2018, rather than from local groundwater. The project is also expected to create roughly 3,000 jobs, mostly filled locally. Now, the important near-term effect may arrive before any chip does. Advanced fabrication sits inside a concentrated market where TSMC, Samsung, and Intel hold enormous leverage. A buyer credible enough to threaten its own factory can change a negotiation. Now, Terafab may never reach anything close to a terawatt. Its first useful product could simply be better terms from the foundries that SpaceX and Tesla still need. All right, now let's move from giant private chip promises to a public weather model that's already helping forecasters. When a cyclone is approaching, hours change who can evacuate and how safely they can move. So what happens when a forecast adds more than a full day of warning? DeepMind and Google Research built WeatherNext Cyclones, which is a model that predicts a storm's track, strength, and size as far as 15 days ahead. A Nature paper published this week tested it across the 2023 through 2025 cyclone seasons. In North Atlantic and East Pacific track tests, it gave about a day and a half of extra warning compared with ECMWF's leading operational ensemble model. That is a major jump in a field where getting a 3-day forecast to match the quality of yesterday's 2-day forecast can take roughly a decade. The model had already shown what that means in practice, too. Last October, it predicted that Hurricane Melissa would strike Jamaica as a Category 5 storm 5 days ahead with 80% confidence. Melissa was still only a Category 1 at the time of the prediction. That helped the National Hurricane Center issue its first Category 5 prediction while a storm was still at Category 1. Intensity has long been the stubborn part of cyclone forecasting. Track predictions improved steadily, while forecasts of how strong a storm would become barely moved. Kate Musgrave of Colorado State's CIRA said that forecasters were surprised by how well WeatherNext handled that hardest dimension. The model also breaks an old assumption about how much detail it needs. It reaches this accuracy with inputs far coarser than the high-resolution regional systems that were once considered essential for forecasting intensity. And it can run up to 1,000 possible storm scenarios from one system. Conventional operations run only around 50. So picture a fan opening across a map here. Each line shows one possible future, and the full fan reveals which outcomes are gathering weight. Farron Allett of DeepMind acknowledges that the model remains a black box for now. Researchers can see that it learned from a huge body of weather data, but they can't fully trace how it reaches every single forecast. And that opacity also gives physicists a useful clue. When WeatherNext beats a system built from physical equations, the gap points towards something that those equations must be missing. So Google is releasing the code and the model waits. Any weather service can run it. The National Hurricane Center already uses it as one input among many, with human forecasters still making the final call. Now that is a strong form of partnership. 1,000 machine-generated futures placed beside human experience, buying communities more time to move when a cyclone's coming. All right, from storms that change direction, let's turn to a virus that changes from season to season. Traditional flu vaccines force scientists to choose their target about 6 months before doses ship. If the circulating strain changes after that choice, then the season is stuck with a weaker match and we get a stronger flu season. Now, can that decision happen closer to the moment that the vaccine is needed, thereby making it less likely that the strain will change very much? On August 5th, the FDA licensed Moderna's mFlusiva, which is the first messenger RNA flu vaccine cleared in the United States. A 40,000-person trial across 11 countries found it was about 27% more effective than the standard flu shot in adults ages 50 to 64. The FDA granted standard approval for that group. Adults 65 and older receive accelerated approval, with Moderna committed to a phase 4 study to confirm the benefit in the oldest patients. The bigger change, though, is the calendar. Current vaccines grow their ingredients through a biological process involving eggs, and that takes time. Messenger RNA gives cells a genetic instruction for making the target protein that trains the immune system. And once that platform exists, changing the target looks more like changing the file sent to a printer. Moderna can move from strain selection to finished vials in roughly 2 to 3 months instead of 6. Now, that shorter window won't eliminate bad forecasts. It does give scientists, though, far more current information before they have to commit. And it also may leave time to respond when a strain does shift later than expected. Access now trails the science, though. A federal court has blocked the Immunization Advisory Committee's usual recommendation process. That recommendation normally opens the automatic insurance pathway, which makes the vaccine free at the pharmacy, and without it, coverage for mFlusiva remains unsettled. That barrier matters to anyone who can't pay out of pocket, and it also belongs to today's coverage machinery, while the underlying platform has now proven itself against 2 very different respiratory threats. The same approach produced a COVID vaccine in under a year at a time of high crisis, and it can now reprint a seasonal flu target in weeks. The approval establishes the press. The next step is making sure that everyone can actually reach what it prints. All right, so that faster vaccine gives us a way to act on biological information. Our final story for today changes how much of that information we can actually read. More than half of rare disease cases still receive no genetic explanation. One reason is simple. The standard human reference leaves roughly 15% of our genome poorly resolved. So what has been hiding in those gaps? On August 6, the Telomere-to-Telomere Consortium published the first complete diploid genome from a living person. Now, diploid means both chromosome sets, one inherited from each parent. Researchers read both sets end to end with no gaps. The donor is known as HG002. Teams from Johns Hopkins, the National Human Genome Research Institute, and NIST presented the work in 12 papers across cell and cell genomics. The benchmark added more than 900 million DNA letters beyond what prior variant benchmarks captured. Those missing stretches contain repetitive and structurally tangled regions where older sequencing methods tended to lose their place. So think of trying to assemble 2 almost identical books after someone has cut both of them into strips. Ordinary sentences are pretty manageable, but a page filled with the same repeated phrase is much harder. Now researchers can separate those 2 books and rebuild both completely. Those difficult passages are also places where genetic causes of disease may be hiding. Now, the same consortium reached a landmark back in 2022 by completing one composite human genome. This week's work resolves both parental copies from an actual living donor independently, including both sex chromosomes. And then there's the cost curve. The Human Genome Project took more than a decade and cost about $5 billion in today's money. A complete genome now costs closer to $5,000. That is roughly a million-fold drop, bringing a species-scale undertaking down toward the price of a used car. Now, this still isn't a service that a patient can request at a counter. Clinical labs still do need new reference tools. Researchers must validate how they interpret the newly visible regions. And health systems need pipelines that can turn those readings into reliable diagnoses. What has been proven here is more basic and more powerful. Both copies of one person's genome can be read without gaps, including the regions that resisted every earlier map. And the method also reaches beyond humans. Companion papers also applied it to the macaque, the marmoset, and the zebra finch. The technique can travel from one species to another. HG002 now gives other labs a standard for measuring their own sequencing work. As those tools catch up, the missing pages that concealed disease can become ordinary parts of the book. All right, closing for today. Who watches the agents? No single company can do it. No sealed review can cover every downloadable model. The strongest answer, then, is a wide field of independent evaluators, public evidence, fast detection, and failures that everyone gets to study. That same test runs through the rest of today's stories as well. Terafab arrives wrapped in enormous numbers and non-binding language. Its strongest near-term effect, then, comes from making concentrated chip suppliers answer a credible threat from their own customers. WeatherNext takes the opposite route. It has already demonstrated the capability and joined operational forecasting, and it is opening its code and weights to weather services around the world. The mRNA flu vaccine has crossed the regulatory threshold, while the insurance pathway still decides who can get it without paying. The Genome Project has made previously unreadable biology visible, while clinical systems now need to learn what to do with those new pages. Across all 5 of today's stories, the pattern is visibility. Agents expose weak boundaries. A public model shows its forecasts. A vaccine platform shortens the gap between a changing virus and our response. A complete genome reveals regions that medicine could not read. Observation held by a few becomes a point of control. Observation shared widely becomes a way to learn faster. That is the hopeful answer here. We don't have to build one perfect watcher. We can build a world where more people can inspect the boundary, test the result, and improve the next response for everyone. See you tomorrow.